welcome to this Isifundi Bite-Sized Corrosion session. So today is the final session in our series on cathodic protection in hazardous environments. My name is Neil Webb, and I'm joined today by Ruan Badenhorst, and we're going to be talking about some of the practical application of cathodic protection in hazardous environments. We've looked at what is a hazardous environment, what are the challenges associated with actually establishing a cathodic protection system in a hazardous environment, some of the design considerations, and then once the system is operating, we had a look yesterday at the monitoring of systems, which is where Ruan in particular has had a lot of experience over the last few years. And so welcome, Ruan, and let's go through some of the practical aspects of operating the CP system in a hazardous environment.
Thank you, Neil. I wonder if I can kick off. I'm intrigued by your statement that CP can provide more than just corrosion protection. Care to tell us a bit more on what CP can offer?
Yes, well, it's an indirect monitoring system, if I can call it that, of integrity. So the whole principle of cathodic protection is that it is providing an electric current through to a protected surface, and the current then prevents the corrosion reaction from occurring, and we monitor that level of protection by means of measuring the potential that is established. As with any electrical circuit, if you've got a resistance and a current flow, you're going to get a volt drop, and we use that volt drop, which we term the pipe to soil potential. So the result of that process is that we have got a record now, because we've been doing monitoring, as we discussed yesterday. We've got a record that the corrosion process has been stifled on the surface of the equipment that is being protected. And we can show from those records that this has now been ongoing. So one of the interesting and more challenging examples that we've had is that of LPG bullets, LPG, liquid petroleum gas. These are stored in pressurized horizontal cylinders, which are buried above ground. You might say, well, how on earth do you bury something above ground? That's very easy. You may put it on a stand and you create an artificial mound over the top, but like a burial mound, except that we are not burying a dead body. We want to keep our body alive in terms of this bullet. The regulations around the operation of these pressurized bullets are quite strict in terms of integrity management. And typically you have to do some kind of a survey once every 5 years or so. I can't remember what the exact regulatory requirements are, in order to show that your pressurized cylinder is still fit for purpose. Now, it's very easy. Nothing's very easy in this environment, but you can purge the bullet, open up the inspection hatch, and jump inside. And you can do a physical inspection from the inside. You can inspect the integrity of welds, but you have no idea, other than doing perhaps some spot measurements on wall thickness, as to what the external condition of the bullet is. And I've actually seen some situations on mounted bullets which were not provided with cathodic protection, where they unmounted the bullet for inspection purposes and discovered significant external corrosion, to the extent that they had to derate, and in fact, this particular situation, they had to scrap the bullet due to external corrosion. So the advantage of the cathodic protection system then is that, provided you've been doing the maintenance and monitoring as you described yesterday, that if you've got those records, then you can show that there has not been any external corrosion, as evidenced by the fact that it fulfills the protection criteria. And that is why it is so important to use recognized codes for interpreting the data. And in fact, we've got case studies in South Africa here where we developed an intrinsically safe system for a mounted bullet. It was installed, the project, if I remember correctly, the project number was in 1998. It took a couple of years for the project to be implemented, but it was implemented in the early 2000s. Those bullets now have been operating for 20 years, and they have not been unmounted once. So there's a huge cost saving associated with the operation of the CP system in terms of not having to, A, take the bullet out of service, which means you now have a non-revenue situation, the costs of purging it to make it safe so that it can be inspected, the costs of unmounting it so that you can physically look at the external. That process is going to take months. So not only is it the direct cost of the operation, but it's a loss of revenue. And although that particular cathodic protection system was probably the most expensive 5-amp cathodic protection system that I've ever designed in my life, the saving to the operator in terms of not having to unmount these bullets way exceeded that initial capital cost.
Yes, that's interesting, Neil, and I can clearly hear that record keeping is very important in that process. So what kind of trends and historical data do we need to look at when we are unmounting a bullet only every 5 years?
In order to prevent that unmounting, we need to show that the bullet has been protected. So if they were unmounting, it would be a physical inspection. What's the condition of the coating? Is there any metal loss associated with corrosion? Those are the things that one would look at in a physical inspection. And you can get that data from the cathodic protection system. Because if you've got the potential records that show that the bullet has been fully protected over the entire period, then you know that there is no significant metal loss. The cathodic protection criterion is such that it gives you less than 0.1 millimeters per year corrosion rate. So at the most, you would expect to have 1 millimeter corrosion after, no, it's not 1, it's 0.01, surely. I'd have to go and have a look at the standard to see, because after 10 years, you don't want a millimeter of corrosion, and you certainly don't get it. So the point there is that from the potential data, you've got evidence that there has been no metal loss. And then from the operating current, you get the results that shows the condition of the external coating, because the current demand on the surface of any cathodically protected system is directly related to the integrity of the actual coating system. And if your coating system starts to fail, you see an increase in the current demand in order to maintain a protected potential. So whilst you are still in the realm of an acceptable corrosion rate, you may well see some degradation in the coating. And really, it doesn't matter as long as the CP system still has the capacity to provide the protection, you can provide increased current. And in terms of the trending, as you asked, or what we see with any coating system, is that you get a slow increase in current over a period of time. And eventually you'll get to an inflection point in the degradation rate where you suddenly start to see a significant increase. It's almost like an exponential curve. If you plot any exponential graph, it looks flat until you get to the inflection point, and then all of a sudden it just takes off. And that's what happens with coating degradation as well. So if you are plotting that value over a period of time, then you can predict when you're going to need to take that unit out for preventative maintenance.
That's interesting, Neil. And on the topic of bullets, what would the frequency of routine surveys be, and what are the preferred methods? Yesterday we were talking about instant off surveys and then the 100 millivolt decay. What would you say are the preferred methods for buried LPG bullets?
They're not really any different to the rest. The routine record keeping from your stationary reference electrodes and so on will always show you if there is a change. You know, if there's a step change. If somebody accidentally shorts out a spark gap, for example, where there's supposed to be a spark gap, I mean, that's a different topic altogether, you suddenly find that there might be a step change in the results. And a step change is usually associated with some kind of electrical disturbance, either something being connected that shouldn't be or disconnected that should be. So again, taking results at infrequent intervals makes it very difficult to tell whether a change is a step change or a gradual change, an actual trend. I firmly believe that the 100 millivolt shift criterion is the more practical criterion to use because of the drift that is associated with stationary reference electrodes. And the other reason for doing that is that particularly if you're using a distributed anode system in the vicinity of a bullet, which is really what one has to do if you're going to maintain an intrinsically safe system. You can't go pumping lots of current into the system. So in order to create the potential envelope around the bullet, you use a lot of anodes, very low currents, and you create a field. And that then enables you to run an intrinsically safe system. If you go and take measurements remote from that system, you will find that the system apparently is not protected, whereas the field, somebody actually once referred to it as a near field system. That's not a universally accepted term, but I think it's a really, really good description of the principle that you're creating a positive field in the ground around the bullet, as opposed to the concept of making the bullet negative with respect to Earth. You make the Earth positive with respect to the bullet. And the net result is the same. You've got this negative potential difference between the bullet and the ground.
You mentioned spark gaps again, and I know we touched on it briefly yesterday. And I know you and Vanessa also discussed the value of insulating flanges and the use of spark gaps at length. Are you aware of any examples where the value of a spark gap has been shown?
Well, it's difficult because until a spark gap fails, it's doing its job. And in fact, what we did find on one of these LPG systems where there was an unacceptable current drain on a system, it was established that one of the spark gaps had been bridged. Not that the spark gap had failed, but that somebody had connected an earth wire on the wrong side of the spark gap, which effectively bridged out the spark gap. And that's one of the challenges with these systems, is the criticality of either isolation or non-isolation, depending on what your design is. What I have seen is not so much the successful operation of spark gaps, so much as the consequence of not having a spark gap. And I shared a picture in our earlier discussions of a burned through flange where a spark gap had not been installed. But there was a situation on a tank farm that I was involved in a few decades ago, actually, where the cathodic protection system in the tank farm had been implemented using distributed horizontal ground beds. It sounds like a contradiction in terms, and it is, because in the various bunded areas of the tank farm, each bunded area had its own little ground bed, but the anodes were not distributed around the tanks. They were in a concentrated ground bed. And the problem with this was that the potential gradients in the soil were very high, and there was a lot of current running around in the system. So the CP systems had been connected with negative connections to the tanks, but what we found was that all the current was actually flowing in the pipes because the pipes represented a better conductor. You know, a steel pipe 200 millimeters diameter is a way better conductor than a 35 square millimeter copper cable. What had happened is that somebody was doing maintenance on one of these pipes, and the pipe had been purged, and the flange was being split. And when they cracked the flange, there was an arc because of the current that was had been flowing in the pipe, and they had a fire as a result because of the hazardous environment. That illustrates two things: that the system design was really at fault in that the current was not flowing where it should have, and also that the operations associated with the maintenance program was at fault because they did not allow for a temporary bond to be put across a flange. So whenever you're working in a hazardous environment and you're going to crack a flange, you should have a bond across the flange. You know, a long jumper cable with magnetic contacts that you can put each side, so that if there is current in there, the current can still flow through the cable and you don't draw an arc. Because DC systems, as you know, you draw an arc, it doesn't extinguish, unlike an AC system where you've got, you're going through zero every 50 times a second.
It's interesting, Neil. I think isolation is always a topic that comes up, especially in a hazardous environment. And I think you've just highlighted the importance of ensuring that careful consideration is being done as to whether you want to do it and if it's done, that it's done right. Neil, you were mentioning distributed anodes, and I know we've talked about them with regards to LPG bullets and vertical storage tanks. There's some debate whether under tank anodes are better or worse than vertically drilled anodes. What is your opinion?
I don't know that you can say the one is better or worse, because it depends entirely on the construction of the tank and the geology of the tank farm site. So given the propensity to use secondary containment now, where you put a membrane underneath the tank, there is only one way that you can prevent corrosion in that situation, and that is with an under-tank anode. And the debate is not whether the under-tank is better or worse than vertical, because the vertical just won't work. So the under-tank anode is the only way of doing it. The debate there is what kind of under-tank anode system are you going to use? And there you're entirely at the mercy, you as the operator, are entirely at the mercy of the manufacturer of the anode system and the diligence of the installation contractor. Because if you have a system, let's say a grid of activated titanium wire that is put in underneath the tank. Titanium wire is a notoriously bad conductor of electricity. So you've got to have a number of connection points in order to get the power distributed uniformly throughout the tank base. And just for example, just maybe putting in, let's say arbitrarily, just say, oh no, well, instead of making one positive connection to the anode, I'm going to make 4 positive connections. Well, that's not going to cut it, because the attenuation in the titanium wire is going to be such that you will find areas of the tank base that are not protected. So you have to have a system whereby you can uniformly distribute the current in that space between the membrane and the tank base. And one of the better systems, as far as I'm concerned, is the one based on concentric loops of what are called piggyback anode wires, where the titanium wire is supplied with an insulated copper conductor that is spliced into the titanium wire at regular intervals. So you may well have 20 feeders effectively, and over and above that, each feeder has probably got 10 or 20 connection points from the copper conductor to the titanium anode wire. So the chances of your anode system failing in that situation are remote indeed, provided, of course, that the splices have been made properly. And typically you need a 3-layer insulation system to ensure that that copper never sees the environment, because if it does, the copper itself will disappear and then you lose your electrical continuity.
And Neil, what is the influence or what is the importance of then the positioning of your stationary reference electrodes? We were talking about remote ground beds and vertical ground beds or distributed ground beds. Your stationary reference electrode would then, I don't want to say automatically, but be in the zone of influence. What role does the positioning of the SREs play in an under-tank anode system?
Well, in that situation, your SRE is definitely going to be in the field of influence of the anode system. One would place the reference electrode as remote as possible from the actual anode wires. So if you've got 2 loops that are, say, 1.5 meters apart, you would have the electrode halfway in between the 2 wires. But even so, the proximity of the reference electrode to the anode as well as to the tank base means that your potential that you measure is definitely going to be affected by the operation of the anode. And so in that situation, you have to be able to measure instant off potentials, and the 100 millivolt shift criterion becomes even more relevant in that situation, because to try and get, say, minus 850 to copper sulfate in an under-tank situation is certainly a challenge.
I think this conversation and this series has highlighted the importance of careful design, taking in actual site conditions, and that even though we are working in hazardous environments, that we can successfully implement CP, and that doesn't have to be this big scary mountain in front of us.
I think that's a very, very relevant point. And, no two situations are going to be the same. So it's very important that whoever is responsible for the design and operation of the system is aware of the intricacies, if I can call it that, of the system. Your plant engineer doesn't have to be a cathodic protection designer, but he does need to appreciate the relevance of both continuity and isolation, and then to know what is suitable for that particular situation. If you've got an above ground terminal with ASTs and you're protecting tank bases, and they've got secondary containment, then you can put as many anodes in the ground as you like. They're going to be of no benefit whatsoever. If you're in an area where you've got low resistivity ground conditions and you do not have secondary containment, but perhaps the whole area has been built on a clay bed in order to prevent environmental contamination, well, then the electrical current will still go through a clay bed, even though it is impermeable to spillage. And in that situation, you can use either remote or distributed anodes. So it is vitally necessary to know the construction details of your system. And also to know that, for example, isolation is not always the right thing. There was an incident a while ago where there was a tank fire which was caused by a lightning strike. It wasn't a direct strike on the tank, but it was a strike in the area because there was a floating roof that had not been bonded out for static prevention. There was then a differential due to the lightning strike between earthing systems. And there was a flashover from two different components, lack of a spark gap or lack of continuity in this case. Both. And the net result was a tank fire, which of course nobody wants.
Daniel, adding on to what you said about isolation, we recently experienced a situation at a plant where a recommendation was made by a CP engineer with regards to isolation due to the risk of creating a spark during maintenance. Now, the problem wasn't that the recommendation itself, but the fact that it raised a concern which could have been addressed at the time, but rather than coming up with a solution, the client simply switched off the CP system dedicated to the firewater system for some odd 15 years. And this in turn subjected the buried firewater system to corrosion and resulted in leaks within the firewater system. Now, had this issue been addressed rather than ignored or put in the corner hoping it would go away by itself, could have maybe been prevented.
Absolutely. You certainly can't bury your head in the sand in this situation. So that's it. We've kind of run out of time. We could carry on talking for ages. So thank you very much, Ruan, for going through this with me.